when we talk about combining capacities, okay, we've seen examples where we have 1-to-1 ratios regardless of their valence electrons, where if they both have, if one of them has 3 extra valence electrons and the other substance needs 3, that is a 1-to-1 ratio. So then we would have something like, I don't know, aluminum nitride. I don't think that even exists, but whatever. Aluminum and nitrogen. Aluminum has 3 extra, nitrogen needs 3, right? If we have something that has 2 extra electrons, valence electrons, and something that needs 2 to fill its shell, again, 1-to-1 ratio, right? When we have something that has a 2 or a 3 extra valence electrons, and we have something that only has a -1, kind of like our aluminum and our fluorine, well, we need 3 fluorines with their -1s, -1 plus -1 plus -1, to bond to 1 aluminum. And when we draw this out, when we talk about combining capacities here, we almost say that an atom of aluminum has 3 actual little hooks coming out of it. That means it's got 3 extra electrons floating around. Okay? And fluorine only has 1 little hook. All right? So how many of these F's am I going to need to actually match up with all of aluminum's hooks? I'm going to need a total of 3 F's to cover all 3 hooks, right? No actual hook can be left out in the open. That means that a hook represents an electron. All electrons must be given away or must be taken up by something else. There can't just be a lone electron floating around. That doesn't work. Okay? So in this case, if we're actually going to draw this, all right, I would make this guy a wee bit smaller. Okay? And I would come and put him up here, and then I would draw another F with a hook, and I would draw another F with a hook, and I would move each of these over here to show that all of the aluminum's hooks are taken and all of the fluorine hooks are being used up. There's no open spaces, no open hooks here. So if we look at this, we say that there is 1 aluminum and there are 3 fluorines, right? So this is not that complicated. It's really easy when something has when something is in group 17 and has 7 valence electrons, it only needs 1. So you can add many of those and bond it to whatever. But this guy's a little bit different. Because for this guy, we've got our aluminum, okay, we've got our Al that's got its 3 hooks, right? And then we have this oxygen here that's got 2 hooks. Whoa. Well, if I bring this over, okay, so if I select this guy, I'm like, wait a minute, these guys can't bond, these guys cannot bond together. Okay, every hook from, every electron or hook from an atom must bond to another atom. It cannot bond with itself. Okay? So right now, as it stands, all right, we've got these 2 electrons which are kind of floating around in no man's land. This doesn't work. It is not a 1-to-1. Okay? So what we end up having here, we'll move this guy, we'll make him a little bit smaller, because we're going to draw these guys out after we do our math. How's that? Okay, and we're just going to move this guy down a little ways, and let's do our math together. If this has, how many valence electrons on its outermost shell? How many does aluminum have? It will have 3 because it is in group 13, right? it will have these 3 extra electrons floating around, right? That's not good. That's not stable. It doesn't want to have 3. It wants to have 8. How many does oxygen have floating in its outermost shell?
6.
It has 6, so it is missing 2. Oh, that's not a 1-to-1 ratio. So just like factoring in math, you find a common factor here. Okay, what do I have to do to 3 and what do I have to do to 2 to get them to have the same number? And the first number we get to is 6, right? That's the first common factor that these guys can have, right? So what do I have to do to the 3 to get to 6?
You have to add another.
I need another 3 plus, correct?
Yeah.
What do I have to do to my negative 2 to get to 6?
We're very clear on this.
How many negative 2's do I have to get 6? To get negative 6?
Okay.
I need 3. So I need another one and another one, right? If I sum this up, it's 6 plus. If I sum this up, it's 6 minus. Those cancel each other out, don't they? So, in total, if I look at this, how many aluminums do I need in my drawing? I need 2 aluminums. How many oxygens do I need in my drawing?
3.
I need 3 oxygens. So what I'm going to do, I'm going to put this guy right here, okay? And I'm going to come up with another aluminum, and I'm going to bond my 3 here, right? And I'm going to move it over so that it can bond with one of those oxygens. Do you see that? Okay, then I'm going to draw another oxygen. And I'm going to draw another oxygen. And I'm going to move each of them in place just to make sure that everything is hooked up. Does this make sense to you? Okay, I know my hooks aren't really touching here, but whatever. So this visual shows you that in order to actually bond aluminum with oxygen and make it stable, you need 2 atoms of aluminum bound to 3 atoms of oxygen. So what is the chemical formula here?
Al2O3.
Al2O3. Now, would I call this dialuminum trioxide? Because there's 2 aluminums and there's 3 oxygens. Would I call this dialuminum trioxide or just aluminum oxide? Which one would I call this? Okay? Am I going to call this, Saved by the Bell. What is this, an ionic bond or is this a covalent bond? It's ionic because aluminum, girls, stop for a second. It's ionic because aluminum is a metal, oxygen is a non-metal. Therefore, what is its name?
Aluminum trioxide.
No, aluminum oxide, right? Doesn't matter that there's 3. The tris and the dis only work for covalent bonds, right? Have a good day.